Hello guys, and welcome back to the PyTorch tutorial series. In the last video we talked about linear regression and the theoretical application of the linear regression algorithm. In this video we're going to implement the algorithm using PyTorch. Before we see a demonstration for linear regression, in the last couple of videos we have seen how to construct a training pipeline for training any kind of model using PyTorch. So let's just recap how to construct a simple model using PyTorch. So the first thing that we have to do is preparing the data. That can be a dataset or a data loader. Second, this will be our main focus in this video. We're going to design a model, and in this particular video we're going to implement the linear regression algorithm, and on the next video we're going to implement the next type of machine learning algorithm known as logistic regression. Third, we must construct a loss function. It could either be a mean squared error or cross entropy. Fourth, we need to construct an optimizer. In the video about optimizers, we have seen how to implement gradient descent or Adam optimizer. Fifth, we have to create a training loop, and the first thing that we have to do inside the training loop would be performing a forward pass to compute the prediction. That prediction could be computed by using the model. Second, we have to use the loss, and we can pass the prediction and labels. Third, we can compute the gradients using the backward pass. And finally, we need to update the weights using an optimization algorithm. That optimizer is the one that we have created on the fourth step. So let's just recap that example, and we will replace the simple function that we had created in a previous video by using the linear regression algorithm from the neural network package. So the first thing that we need to do is to import Torch and the neural network module. Then we need to create the data and the labels. So here we're going to use a list of numbers from 1 to 4 for our data, and for the labels it's going to be even numbers or a multiple of x by 2. So this is a simple demonstration that we used in the previous video, where we created a simple linear regression algorithm in which the label is just multiplying x by 2. So first we're going to see how to construct the whole training pipeline by using this data and using the simple function 2 times x. The third step would be to initialize the weight, and here we're just using zeros for now, but it would be appropriate to initialize the weights by using random weight initialization or other types of weight initialization techniques, but for this simple demonstration we're just going to use 0. And the data, the label, and the weight, all of them must be converted into tensors if you want to use the neural network module. Let's just run this code. Second, we need our forward function, which is going to be the weight multiplied by x, and this is going to be our model prediction. So this is the model that we're going to replace when we want to implement the linear regression algorithm. Let's see the prediction from our model before we start the training procedure. Now you can see, since our weight is initialized to 0, the prediction before training f of 5 will be 0, because 0 multiplied by any x, in which this case the test case is 5, will be 0. Third, we had already defined a custom loss function before, but now we're going to use the mean squared error loss from the neural network module and assign it to the variable loss. Third, we're going to initialize the learning rate to 0.01 and the number of iterations to 100. Here we're initializing the optimizer to stochastic gradient descent, and the first parameter must be the weight and the second has to be the learning rate. And when we pass the weight, since it's just a tensor of 0, we need to pass it as a list, so don't forget to put the brackets and put the w variable inside the square brackets. Finally, we're going to run this for 100 iterations, and the first thing that we need to do is to perform a forward pass, and we're using the custom defined function forward that we have created here. Once we get the prediction, we can use the prediction and ground truths and pass it as arguments to the loss function that we have initialized here. So still the same as before, and here we need to compute the gradients dl by dw by using l.backward function. Finally, we need to update the weights by using the optimizer that we have created here and call the step function. Then we need to change the gradients to 0 before the next iteration by using w.grad.0. Since w is the weight, grad is a parameter, grad will give us the gradients, and 0 underscore will replace those gradients by 0 before the next iteration, and we're going to output every 10 epoch. As you can see, the loss is decreasing to 0, and we can see that the appropriate weight is 2, and our model is getting better in each epoch, and finally it gives us the appropriate weight. And now if we want to make a prediction using the forward function again, since our weight is updated, now it's 2 times 5, so when we use the test case 5, our model is predicting that it's going to be 10. Now that we have seen a simple demonstration using a custom defined function forward, we're going to replace it by using the linear function from the neural network module to perform the linear regression algorithm. The first thing that we need to modify is to convert the list that we have created before and put each number inside of square brackets. We're doing this because PyTorch accepts the tensor in the form of number of samples by number of features, so the dimension has to be needs to have n samples rows and n features columns. So when we are putting the numbers inside of square brackets, we're saying that each number is a different training instance, and we need to do the same for the labels. Now we don't need to initialize a weight because the parameters will also be monitored and created by the linear function from the neural network module. So we're going to comment this line out. Here we're still defining a test case of 5. Before we were just using the number 5 as a test case, but now we need to convert it into a tensor because the shape will be changed. Now, in order to see the shape of our tensor after this modification, we can call x.shape, and we can see n samples and n features. We didn't run this line of code, so let's modify it again. Now the error is gone. Here we can see that the shape is 4 by 1. It's telling us that X has 4 different training instances. So each number is considered as a unique training instance, and 1 is telling us the number of columns. So for example, if you have different number of features for each instance, then you can just modify and add more numbers inside the square brackets. So you just need to so the second number represents the number of features that you have, and the first dimension indicates the number of samples. So we're going to comment out the forward function that we have defined before, which was the simple function w times x, and replace it by the linear function from the neural network module. And the linear function requires 2 arguments. The first one is the input size and the second one is the output size. So the input and output size just represents the input to our model and the output dimension of our model. Since we are inputting one number in each case, so the number of input features is 1, and our model is also predicting one number in each case, so the output size also has to be n features for this simple demonstration. Now when we run this line of code and make a prediction before training and pass x test instead of 5 and call the .item method, we can see that the prediction from our model is now 4.097. This is because our simple linear function has not been trained, and it's just using random weights to make the prediction. If we want to see the parameters of our newly constructed function, we can use the dot parameters function, and we can call it using the model variable we have created here. So this gives us a list, and it says that the parameters contained inside the model are the weight and the bias. So the first tensor is the weight, the random weight that was initialized by the linear function, and the second one is the bias. Here we can see that requires grad is equal to true, which means that it's keeping track of these variables and updating them when the training begins. So the rest of the steps are similar to before, and here we're creating the loss and initializing the learning rate and number of iterations, and the only modification that we need to make here is instead of using W, we have to use the model dot parameters, because this is a newly created parameter that we are using, and we need to pass the learning rate as a second argument to our optimizer function. Then we will start the training procedure. Here, instead of using the custom defined forward function, we're using the linear model that we have created here and passing the input as an argument. Then this function will give us the prediction from our model. So this step is the same as before. Here we're using the label and the predictions in order to calculate the loss, and here we're computing the gradients by using the backward function. The final step would be to update the weights using the optimizer.step method and zeroing out the gradients before the next iteration. Finally, one more modification that we need to make is to use the model.parameters function in order to get the weights and the bias, so that we could print out the weight. Here we were just printing out the W in each iteration before, as we can see from this line of code. Now our weight tensor has a different dimension, so we're going to use indexing in order to access the first weight. So this is for the first row and the first element. Then we need to call the .item method. Here it's giving us the same results, but the previous one was more accurate and giving us the correct weight, because it was assigned by us, so it's clearly easy to modify. But here we're using random initialization of weight, so it takes some time to get the number 2, but on the 91st epoch it's getting pretty close to that number. So after getting the weight, we can use the test case in order to see the prediction after training. So the prediction from our model by using the test case 5, the number that we would want was 10, but it's giving us 10.121. So it's pretty much the same, but if we use if we increase the number of iterations or different initialization of the weight, that we might get a more accurate result. So the second thing that we can do is to create a class known as Linear Regression. and this will extend from the module class inside the neural network package. So whenever you create a model using PyTorch, it's mostly recommended to create your own class and extend it from module and define the layers inside the initialization. So this is the same as before, where we've used the linear function to construct the model, but now we're using our own class and we're initializing the self.linear layer and assigning it the linear function. Here on the initialization, we need to pass the input and output dimensions as arguments. Here we have a function known as forward, and we need to pass the input as an argument here, and we can use the linear function that we have created here, which was initialized to nn.linear, and pass the input as an argument. Once you have created this class, you can just replace this step by using our newly defined class, and we're going to create an instance of this class, and we need to provide the input size and output size as arguments and assign it to model again. So let's run this line of code. Finally, the rest of the code will be the same as before, but in this case we're just using the newly created class and replace the one that we have created before, and let's see if there is any difference. So it's getting better. It's giving us a different result from the one that we have used previously, but the weight is getting close to 2, and when we use the test case of 5 again, it's getting close to 10, so it's heading in the right direction. So when you initialize the weights, it's going to give you different results, because in each case it's using random weights. So that's one of the reasons you're getting a different result than the one that we have used before. So in order to recap what we have covered so far, first we used the linear function from the neural network module. Second, we created our own class, and we saw how to instantiate that class in order to perform the same operations that we did before. So this is pretty much the way that you construct a model using PyTorch. Since our linear regression algorithm is very simple, we don't have a lot of layers, but when you create more complicated models, you have to use this method in order to create your model. And whenever you do that, you have to extend from the module class of the neural network module. The final thing that we need to cover is, instead of creating the input and output by ourselves, we're going to use scikit-learn's regression dataset in order to create some samples for us, and we're going to use that to demonstrate the linear regression algorithm. So everything is the same as before. We will be importing Torch and the neural network module, but we need additional packages such as NumPy and sklearn. And from sklearn we're going to import datasets so that we get a regression dataset, and we can also import matplotlib. So first we need to prepare our dataset, and we're going to use the make regression function from the datasets package. And here we're going to create 100 samples, and each sample has one feature. So the dimension would be a 100 by 1 with 100 rows and one column. And we don't need to worry about these arguments for now. The first step would be to convert the double to float, then to a PyTorch tensor. So the x and y that we get from the make regression function are going to be double, and using a double data type would complicate things when you create a PyTorch model. So the first thing that we need to do is to convert the double data type into float, and we can use the asType method and pass in p.float32 to convert x and y into float first. Then we need to convert them into a torch tensor by using the from NumPy function. We have covered in a previous video how to convert a NumPy array into a torch tensor by using different methods from PyTorch, and from NumPy is one function. So the data that we are getting from make regression is a NumPy array, so that's why we're converting it into a PyTorch tensor. And remember that PyTorch requires the dimensions to be number of samples by number of features. Let's run this line of code first. And this is the data provided by the make regression dataset, and after being converted into PyTorch tensors. As you can see, each instance has one number of features, the same as before. The second step is to convert the shape of y. Remember that the dimension of y is still 100, and it wasn't changed into 100 by 1. So we have covered in a previous video how to reshape tensors by using the view function. So we're using ytrain.view, and the first dimension will be ytrain.shape0. Ytrain has initially a shape of 100, so this would be 100, and then it's reshaping it into a 100 by 1 tensor. Now the input and output have the same shape, which is 100 by 1. And now if we see the number of samples and the number of features by using xtrain.shape, it's 100 by 1. Now we have finished getting our data and processing our data so that it has the appropriate shape. Then we have to create our linear regression algorithm the same way as we did before. Now here the number of features for the input size is n features, so this is the same, and the output size is also n features. We can also replace this one by using n features. It's the same as before. Then we pass the input size and output size into the linear function. Once we have created our model, the rest is the same as before. We need to initialize our learning rate, define our loss, and create our optimizer. And don't forget to pass model.parameters as the first argument to our optimizer and the learning rate as a second argument. Finally, we can start our training loop. The number of iterations is still 100. Here we need to pass xtrain as input to our model, and we can get the prediction from our model. Then we pass the label and the prediction from our model into our loss function. Then we compute the gradients by using the backward pass, and we update the weights, and finally we zero out the gradients. So here we're seeing that the loss is actually decreasing, and if we give it more time it would get less and less. But you can notice that our loss is significantly high on around the 10th epoch, and by the time we reach the 100th epoch it's getting less and less. But we want to head into 0, so one thing that we can do is increasing the number of epochs so that we keep decreasing the loss until we find a local minimum. So it's heading in the right direction, but you could improve the result from our model by changing the learning rate and the initialization of the parameters. And also we haven't done any pre-processing of the data. Remember when we talked about the assumptions for creating a linear regression algorithm is pre-processing the data. So this also has an influence on the loss. Finally, we can plot our data together with the prediction from our model. So we're using the PyPlot module in order to plot our data. So the first thing that we have to do is to pass xtrain into our model and get the prediction from our model. Then we need to detach and convert it into NumPy. The reason that we are detaching it is to stop it from being tracked. Whenever you are evaluating a model, you need to detach the model so that the parameters are not being tracked. Because remember, any kind of operation that you are performing is actually being added into the computational graph unless you explicitly detach the model from that computation graph. So since we do not want the parameters to be tracked, we have to detach it first and convert it into a NumPy array so that we could see the result using matplotlib. So the tensor is being converted into a NumPy array Once we get our prediction, we're going to use a line plot to show the prediction from our model. Finally, when we show the results, you can see that the line is pretty much following the data distribution, and it's getting closer and closer and approximating the linear path. But this can also be improved by increasing the number of iteration and letting the loss decrease to 0. This could help us to find the appropriate line that fits our data distribution. That's all for this video, and we have covered a lot of concepts regarding the linear regression algorithm. In the next video, we will start covering the next type of algorithm known as logistic regression. Thank you for watching this video, and make sure to like and subscribe. Audio Jungle.